My name is Markus van Almsick. I'm a member of the image processing and signal processing team, and my talk title is Neural Networks for Images. It's the same title as last year, but it's a different content. Essentially, it's part 2, not about image classification, but about how to generate images and how to do unsupervised learning. Welcome to the talk about neural networks for images. This talk is meant for people that do know Mathematica but don't know neural networks, essentially. So it's a little bit different than the usual talks you get here, because usually if you get, let's say, go to finite element methods, we assume that you know what finite element methods is all about, and we just tell you how to do it in Mathematica. But my conception, my impression was that lots of people know Mathematica at this conference, but know not so much about neural networks. So we'll just turn the whole thing a little bit around, and I'll talk about not so much about the framework. This will be done in other talks during this conference, but I'll talk a bit more about neural networks, specifically those that apply to images. Maybe a quick question up front. Who has trained a neural network in the audience? Well, okay, maybe that concept was not so good, 50-50. We'll see. Okay, so this was the first topic of this outline, what this talk is not about. So it's not about the framework as such, it's about the networks being used. I will quickly mention classifiers because I'll build on them, but as I said up front in the abstract of this talk, I will try to go beyond the ordinary classifiers that we have in image processing and neural networks that tell you, oh, this is a cat, this is a dog, and so on. But the next topic I'll be addressing are generators, so those neural networks that generate images and how it's being done. Then I'll talk about autoencoders, encoders that work without having a supervision, without having tagged data. So the machine itself tries to figure out how the structure, how the statistics is about in the data structure of the image. This also applies to variational autoencoders, though they have an extra twist I'll be talking about. And then somewhat the holy grail nowadays are generative adversarial networks, or in short, GANs. And this will be the last topic I'll be addressing. And the UNets, this will move upwards a little bit. That's the wrong order here in this outline. So this is roughly what I try to cover, so it's quite a bit. And I, by the way, work here on version 11.3. I try to, not to be brave this morning. I'd like to keep it safe. And so all of this, if you have 11.3, should be possible on your computer. And secondly, what I do, though, is just in very few cases, I'll use a GPU. So this, what you see up here is an external GPU attached to my laptop. If you have a desktop with a GPU, it should be already inside, and that allows me to speed up a little bit the training, which is somewhat almost mandatory if you'd like to experiment a little bit and see how things are working. So quickly, what I won't talk about are classifiers. Classifiers, especially in image processing, usually take an image in, which is here on the orange side. Lots of neurons that are activated according to the pixel activity that they are assigned to. And then that activation works or is being transmitted through the network. And at the end, you'd like to have essentially just a few neurons that are being assigned to certain classes. And depending on the activity of those neurons, you have then a class identification. This is here a very small convolutional network. You just have a few convolutional layers with the corresponding ReLUs. Then I flatten the whole thing, a fully connected layer, another fully connected layer, softmax. That's it. And then it's always interesting to see, if you do experiments, how many parameters do you have to train, because that roughly tells you the complexity or the complexity of the function that you essentially like to fit. Because training a network is very much like fitting a function, except that you are working with functions with lots and lots of parameters. In this case, this very small network already has 150,000 parameters. And if I were now to start running this, okay, this is already, this system does not appear. Okay, so it doesn't, this is a typical thing that happens. I can't train this in real time, so you have to bear with me. I did play it safe, though I did save the stuff up front, which also doesn't seem to work. Now this is set symbol failed to protect. Well, it did seem to work though. No. Hold on. Yeah, but it takes 5 minutes. It's just a few things that I can do this way. And it's as soon as I leave my desk, bring it over here, stuff like that happens. It's unfortunately. Notebook directory. That will crash the machine. Yeah, so this is unfortunately, Apple doesn't go along very well with NVIDIA. I need an NVIDIA GPU. And they make it a little slightly difficult for you to work on this. Okay, so I'm back in business. I did load all these trained networks beforehand because this kind of stuff usually happens when you demonstrate something. So, okay, when you train this, you see essentially if you have training data and test data, you usually see two lines. The red line is basically the loss of the network that you have defined that's being minimized, and then the blue line, which is the more important line, basically tells you if this training that you achieve here, if that also translates to test data, so to data that hasn't been seen by the training algorithm. And if that keeps going down, that's fine. Once it stays up here, you're essentially overfitting, and that's not so great. But this is still in the good ballpark. Here you essentially have the error rate, which is way down there. So this classifier seems to work, and I can nicely apply it, and I can get the accuracy, the error, and so forth. And last but not least, the confusion metric. So that was a business up in the very early days when we were shipping image identify, which is essentially the same concept, just a little bit bigger. More images, larger images, a larger network. Okay, but in order to have more fun, you can also generate images with neural networks, and essentially all you do is, in a way, turn the thing around. Basically have a network that starts with neurons that depict classes or certain types of images, and then you deconvolve, or actually it's a transposed convolution. So a network that becomes bigger and bigger, and at the end, the neurons in your network represent the pixels in your image. And so if I were to generate now a generator network that looks like this, you have basically a unit vector layer going in, which just activates 10 different neurons. And then you have a linear layer, fully connected layer, increasing the activity over 256 neurons, then up to 512 neurons, and then you reshape it into an image and have a deconvolution up all the way to 28 times 28 pixels. You again have pretty much the same network as before, but just in an inverse manner. Again, 153,000 neurons to train. And if I now train this, which I assume doesn't work, just testing, still doesn't work. And still, okay, this is not reading, so I have to get this by hand. Then you have a generator, and the generator allows you to just put in numbers, initial activations, and essentially at the very bottom, let me scroll this up a little bit, you then get an output. Okay, so the idea is you can generate images, you can classify images, and then you can just basically hook it up together. And that gives you what's called an autoencoder. So the idea is to have a network that analyzes the incoming image and then produces an outgoing image based on that. The nice thing about an autoencoder is also that it can be used for unsupervised learning. Unsupervised learning means you basically don't have images that comes with a tag saying this is a cat, this is a dog, or whatever, but just images of cats, of dogs, of zebras, whatever. And in order to create a loss now, you just don't have to compare the incoming image with a tag here somewhere in the middle. But what you do is you just say, okay, For example, if this is an autoencoder, I want to make sure that this autoencoder reproduces the image so that the original image coming in also comes out. And this is a little bit tough because you have here what's called a bottleneck. You basically make the machine try to condense the information in the image so that it can be passed across these few neurons and then be rebuilt. And so basically you urge the network here to find some kind of representation that is pretty informative about the incoming image. And you can also increase the difficulty a little bit by, for example, saying, okay, the images that I send in are also corrupt in the sense that I put noise on them or that I cut away a few things so that the network learns to undo this corruption. Here I built an autoencoder with just 5 neurons in the middle, so it's not one-to-one here. This is just depicting the concept. And so this would be the autoencoder. Again, you can see you encode something, then you just have 5 neurons, you decode it, and the loss is basically a comparison of the input with the output. The input coming here and the output coming from the decoder, feeding into the loss function here and producing a loss. So again, I don't waste time. This, by the way, just as an order of magnitude, it takes about a minute or 2 to train on a GPU. So in principle, one could do this live, but with just 20 minutes or 25 minutes to go, I rather not waste this time. Result. And what I get now is an autoencoder net. I can extract from the autoencoder the encoder part, which I do here via net extract. And then on top of it, I have to attach a net encoder, which basically converts an incoming image into an array. And I extract here the decoder part, and then I can play with it. For example, I can say, well, take the encoder, apply it to a digit, like here, and it automatically generates now the activity of those 5 neurons in the middle of the autoencoder. And then I can take that code and reproduce the image. And you see, well, it's not exactly identical, but the essence is there, roughly the thickness of the digits and the type of digit. And of course, I can combine this. I can combine encoder and decoder. And the benefit you have here is now that this encoder and decoder, since it tries to read out the essence of the digit, is pretty robust against noise. So if I add now noise to these digits, quite substantial noise down here, I can just send it through the encoder and decoder and automatically retain the digits. And please forgive me that I'm doing this all on very simple examples. That way you can play with it. Of course, this all applies to larger images as well. Okay, then since you now have automatically learned something with an autoencoder, you can actually take that unsupervised knowledge that you have gained and apply it to some other task. For example, you could take the first 2 layers of the encoder that you just generated with the autoencoder and use it as a feature extraction layer in another classifier, for example. The benefit of that is that, in essence, I only have to reattach a new kind of last few layers to classify the features coming in. And that can be done with much fewer data points than I usually would have to use. So what I do here is I create a classifier part, so the end part of a network. I just quickly look how much information that's needed to be trained. And you can see the classifier back here is basically easy to train. It just has 2,570 parameters in contrast to the 150 that the entire encoder just had a minute ago. So what I can do is I can combine this into a classifier. I take the first few layers of the autoencoder that I just trained without labels, and now I just attach the few classifier layers, and then I can put this into a net train command, and it now retrains the whole thing, but just with 1,000 data points. So instead of 50,000 digits to run, I just need here of the order of 1,000. And what you also see here is I make sure that all the first 6 layers are not being trained by setting the learning rate multiplier to 0. Only the remaining ones are being trained, and that then runs a little bit. And So I have to get here the result again, get. And that way I get a classifier like this, which I have trained like this. You see, you do overfit because I have very few points to work with, but I can apply it and it just works fine. I get down to an error rate of less than 5%. And I won't waste now time. I just, for the completeness sake, I did also attach here the whole thing without using the pre-trained feature extractor, and see how well I do. And you can see that you basically gain 1 to 2% error rate because of this transfer learning, because of the detaching from the autoencoder the feature layers and reattaching them here. So let me skip this because time is of the essence here. So now another autoencoder. It's slightly different. It's called the Variational Auto-Encoder. And the additional benefit here is the following. What we had before was basically an autoencoder that just took an image, somehow compressed the data into a few neurons, and then was reconstructing the data again. But there was no influence in how it would construct those 5 neurons or how it would encode. It could do it in any way it would like to. And if you would like to maintain a certain consistency, a certain nice feature space here in the bottleneck, you have to impose a few extra constraints. And the constraint that a variational autoencoder tries to impose here on the bottleneck is that the statistics of the activity of these neurons should be a Gaussian distribution. So the activity should be around 0, and you make sure that the statistics behaves pretty much like a normal distribution. And now the question is, how do you do that? Because that's the tricky part. Well, the decoder part is essentially the same as we had before. You have a linear layer, then you reshape it, and you have a deconvolution layer, and so forth. The tricky part comes with the encoder, because the encoder has to produce kind of random variables or latent activities that have this normal distribution. And in order to obtain that, you do not create just a layer of activities, but you create just the properties of a Gaussian distribution, which is you create the activities of the intermittent neurons by a mean and by a standard deviation, or in this case, a logarithm of a standard deviation, just because it involves less computation, essentially. And these are the two informations that you generate. And then from these two, you generate a random number according to a normal distribution and feed that into the decoder. So it's a kind of a random process that is being driven or stirred by the encoder. And all of this, well, this is something you probably have to do then once you get the notebook, which will be uploaded, by the way, right after the talk. You can generate this this variational autoencoder. And well, if I train that, and since training takes too long, I'll load it in quickly. So I get this encoder, and the encoder has now the nice property that it tries to generate a kind of a continuous manifold of properties. That's the advantage of a variational autoencoder. Because of the statistics that you impose, you have to make sure that neighboring properties are located next to each other. So the encoder essentially generates a mean and a standard deviation. You create the mean, you put that into the decoder, and that generates then an output digit, like here in this case, a digit 6. And the whole thing doesn't look like much, but if you then generate a whole array, or the whole manifold of activities in these just two neurons, by the way, in the bottleneck, you see that you generate a kind of a continuous distribution of digits, like here's a center of 7 that slowly changes into the digits 1, 8, 0, 6, 9. Only the 4 probably needs a little bit more training. It's very much like the 9. And now that also allows you to just, if you move around in this space, to basically interpolate between features. You don't interpolate between pixels anymore. Okay, this, by the way, is very nice if you were to estimate a pose. Let's say you have lots of pictures of people posing, and in order to identify the parameters of the poses, this is how you could go about. All right, I just quickly want to mention one network that's, by the way, not yet in the repository. It's a UNet. A UNet has a certain resemblance. Okay, there we go. Has a certain resemblance with autoencoder. If you, come on. If you look at it, basically it's like an autoencoder that encodes certain features, then has a connection, then encodes even further, and so forth. Here we go. So this is the input, and essentially you decompose an image further and further and further until you get to a very low resolution, and then you reconstruct it again. And essentially, this is great for translating images. Translating means, for example, if I have an image that I'd like to segment, then I'd like to translate the image from an image into a segmentation. And this you can, for example, do with this particular network by running it through this net. And well, maybe I don't activate everything. I'll just show you the result, since I don't have GPU support here. And it allows you then to segment, for example, microscopy images automatically without having to teach your machine all the details, all the features to look for, and so forth. Segmentation means basically if you have an image and you'd like to segment the foreground versus the background, for example. Here, to, for example, segment all the cells to get the outline of a cell. That means, yeah, you may want to call it layer as well. Just fine, yeah. It's going to be uploaded where all the notebooks for the talks will be. What is it called? It's Pathable, right, exactly. So this will take another half an hour because I was working with version 12 and I decided to switch shortly beforehand, so that's why. Okay, and last but not least, let me quickly mention GANs because they are the hot topic now. GANs, in a way, also train generators. So basically, you have a generator network like here. But if you don't have labels, what you could at least, instead of just doing an ordinary loss, you basically also have a network which functions as a discriminator. And a discriminator basically has the following task. I generate images with the generator, starting with some random input. And these images have to look very much alike like another set of images. And then the discriminator has to tell, is this now a fake image or is it a real image? And both of these networks have to basically play against each other, which means that the generator has to forge images and tries to get better and better. And the discriminator has to basically get better and better to tell apart what's forged and what's not. And so this you can also run in Mathematica, but this takes a little bit too long, so I'll skip through the code here. And at the end, you end up with a generator, and this, unfortunately, is always very hard to train. And you get images like this here. I should probably train a little longer, where the out of the blue, basically, the generator learns how to forge an 8, a 9, a 0, a 5, and you slowly get to the point where the images that you make up look almost identical to the ones that you have as a comparison. And this is basically what's behind those cyclic GANs that we have in the net repository, and the next talk will be addressing those. If you have two unpaired sets of images, like a set of photos and a set of paintings that roughly depict the same thing but of different style, then you can generate mappings that take you, for example, from a photo to a painting and back. And there you have now, again, adversarial network, basically a discriminator. One discriminator trying to figure out if this is a photo or not. So if this mapping screws up and converts a painting of Monet into something that should look like a photo but doesn't, this discriminator would kick in. Vice versa, if G maps something to Y and it doesn't look good, this discriminator would kick in. And in order to make this a cycle, I also make sure that whatever I generate here has a certain resemblance with what's at the origin, because if I concatenate G and F, then I should get something out that resembles the original image. So a little bit like an autoencoder. And these are GANs, and just to end here on an interesting note, I'll just load here an image. So this is a painting of, oh gosh, what's going on here? Okay, sorry, this is blowing it. I don't know why image dimensions doesn't work right now, so this is a killer. I'm sorry for that. But basically, you can create images like that, and then they are being converted to photos and vice versa. And I will skip this now because this will also pop up in the next talk by Tusita and Matteo, and so you'll get an impression of how this works as well. All right, this brings me to an end. Thanks for attending, and happy computing.